the Kepler Space Telescope. We will find out why is it interesting in small telescopes. I will come to this point. And the main result of this paper is that significantly larger fraction of slow rotators were found than previously reported mainly from ground-based observations. So it seems that there is some problem with in this sense, there's some problem with the ground-based observations. So they don't get the same statistics as we would get from a space observatory. Okay. So let's just take the ones which were those TNOs which have a previously determined rotation period. So from the 66, there were 15 TNOs which were measured from ground-based observations and from the Kepler observations, and only one period matched, which is not very reassuring in this sense. So this was a contact binary, by the way. So if you look at the statistics of the trans-Neptunian objects with any kind of light curve information, we have roughly 100 TNOs for which we know this kind of information. And the reliable rotation periods are known for, say, 10 to 20 objects. So it's a small fraction, basically. So, so it raises the question whether the rotation periods reported in the literature are reliable at all. Okay, so are there any biases in the ground-based period determination? Well, of course, what we want to determine is the period and the amplitude, at least. Not talking about the shape of the light curve. Of course, we want multiple epochs, multiple colors if possible, but in general, we want period and amplitude. And before the mid-2010s, majority of the asteroid light curves were from ground-based observations. This was also true for the trans-Neptunian region. And in the ground-based observations, there is a so-called reporting bias. The reporting bias is that non-detections are usually not reported. Non-detections mean the amplitude is too small, or the rotation period is too long, so we don't see a real change during the observations. And there is also a so-called single night bias. So the good targets have a rotation period which fits into a single night. So this is very clearly seen from the earlier average rotation period of trans-Neptunian objects, which was roughly 8 hours. So 8 hours is that in a longer winter night, you can easily fit into the observations. And these problems were not really recognized until recently. So we needed something that can continually measure longer than this 8 hour or whatever, say, 1 day period. And the K2 mission of the Kepler Space Telescope was a pioneer in this sense. So it shows not only for the trans-Neptunian objects, but for all small body populations, that the fraction of small rotators are much larger than previously thought. But of course, K2 could not observe, or Kepler could not observe everything. I mean, for Kepler, you needed this. It was a special case because only the pixels on the chip were downloaded, which were previously selected. So passing by asteroids, data of passing by asteroids could not have been obtained. So yeah, but now we have tests, and this is very promising for main belt asteroids. Now in the first release, we had something like light curve and precise periods for 10,000 asteroids, roughly. But for most trans-Neptunian objects, even for the brightest ones, these are too faint for TESS. TESS is a very small telescope. So in most trans-Neptunian object cases, we still have to rely on ground-based observations. Yeah, I mean, the problem with this is that you cannot ask for observing time on a, say, on a 4-meter telescope, on a very large telescope for weeks. You just want to observe the same asteroid, trans-Neptunian objects for weeks with the same large telescope. It's simply impossible. So what you can do is to use many small telescopes and more or less sporadically measure rotation periods if the rotation periods are not very short. So the question is whether these kinds of observations, if you bring everything together, can provide a single rotation period, considering that they were maybe taken different filters. They have calibration problems and all the problematic stuff that we could have if you use different telescopes. Okay, so let's get into the case of ERIS. So ERIS was not observed by K2, unfortunately. And yeah, it was very nice to see that the previous works reported rotation periods in the 3-hour to like 15-day range, and all with 99.9% confidence. So everybody who observed it was very confident that this is the right rotation period of ERIS. Okay, so of course it cannot be that all these rotation periods are true. So what is the true rotation period? Or why is it interesting? It's interesting because it's a binary system. It has a large satellite. Well, we guess that it's a large satellite called Dysnomia, with an orbital period of 15.8 days, roughly. So the physics, what we were interested in basically, is that the actual rotation period of ERIS can tell us about the tidal evolution of the system. So the satellite, we know that the satellite orbit is circularized. But if you, okay, so circularization happens first in a tidal evolution of a binary system, and in a like 1-2 orders of magnitude later in time happens the tidal locking of the system, depending on the mass. Well, in this case of the moon, because we are talking about the tidal locking of Dysnomia, the primary, or the material strengths, and then all these kind of parameters. So ERIS may still rotate fast or slow. Fast means that the moon does not have enough mass to slow it down. If it's slow or tidally locked, then the moon had the mass, or the material properties of ERIS are on that range that allows it to lock the rotation of ERIS. Okay. So we had some test measurements, but it was very, it was, yeah, you can see this here. It was a very crowded field, and we have many problems with getting a precise photometry, so we could not unambiguously identify any period. So we collected a large amount of ERIS light curve data obtained typically with small 1-meter class telescopes. Many from Spain, Colorado Observatory, Sierra Nevada Observatory, La Hita, also the Concole Observatory, 80-centimeter telescope, and so on, and data from the literature. So that typically we had a few data points per night for a few consecutive nights, separated in some cases by years. And even in some cases, the night-to-night calibration was problematic. The night-to-night calibration can be problematic because your target is moving and you are not using the same reference stars. So what we did was that we made so-called blocks of observations where the same reference stars could be used for the photometry. It's typically for ERIS, because it's moving slow, it's like 2, 3, maximum 4 days, depending on the size of the chip and so on. Okay, and we assume that the light curve amplitude is the same in all bands. Of course, these were taken in different bands, in R band, in clear band, in whatever. And we allowed 0-point variations between the blocks, because what we saw was that there is a substantial difference between the average level of the blocks, and it cannot be just due to the rotation of ERIS. It's a calibration problem. So we allowed this as a free parameter, and we looked for rotation periods in the range, so periods longer than 1 day, and we expected that the light curve amplitude is small because we did not really see large variations. So, and we run a residual minimization algorithm. So this is a test, what we did, assuming that the system is tidally logged. So it's like this is 15.8 day period, using a simulated light curve with this period spread exactly at the times when the real observations were done, and adding noise and so on. And it basically gave back the right rotation period. So it was a kind of reassuring that this works. And when we run this for the real data, of course, it's much more structured than the simulated one. But the deepest minimum is at 16.2 days, very close to the tidally logged rotation. So it says that it's very likely a tidally logged system. Yeah, here are some fits. Just a sample from this whole thing. Okay, but it seems that it's tidally logged, but can we somehow confirm it? Yeah, we can actually, because if you take Gaia data, the period is so long that now it's possible to see it in Gaia data. If you take other TNOs with shorter rotation periods, presumably shorter rotation periods, it's difficult. But the Gaia data actually points exactly to the same rotation period, and also says that ERIS is tidally logged. And by the way, it gives almost exactly the same light curve amplitude as our ground-based observations. So we were very happy to do that. This came out, of course, and a few days later, a few days after our paper appeared in AstroPH, we were contacted by an American group, and they gave a completely independent confirmation of the tidally logged rotation of ERIS. So they used 6 months. Well, they had a somewhat larger telescope, the 6 months campaign on a Palomar 60-inch telescope. That's, yeah. 1 month Hubble data, and the 3-year dark energy survey data, and they merged everything. And then they got this period, which is very close to the tidally logged rotation, with exactly the same light curve amplitude that we got. Okay, great. So what does this tell us? So, okay, we know that the ERIS is, the rotation of ERIS is logged, tidally logged, it's fine. If you run some very simple tidal evolution models, well, of course, you have to make some assumptions how the system was formed and what was the original rotation period of ERIS and so on. But basically, all runs of this model, I mean, these are here like 10,000 or even more runs of this model with different initial conditions. What you get is that the tidally locked state can be reached if the mass to system, if the mass of the satellite or the satellite to system mass ratio is like 2 to 3%, and the density of dysnomia is in this range, so roughly 2 grams per cubic centimeter, which is an exceptionally high value for an object in this 700 kilometer size range where dysnomia, so the satellite of Eris, should be. Okay. And yeah, conclusions. Yeah, I'm a bit late, I'm sorry. So it seems that, well, the Eris is a good example that combination of data from small telescope can lead to interesting science. And there are still a number of interesting trans-Neptunian objects with not so precise rotation periods. And it matters a lot in tidal evolution models, comparison phasing with thermal emission light curves and occultation shapes, which if you know about the Wilawer case, for example, the multiple rings and so on, and the shapes of the Wilawer itself, this is a very interesting question here. And of course, also again for Wilawer and for Haumer, stabilizing ring material via spin orbit coupling, for example. So yeah, so that was it. You can read more in this paper here. It appeared in Astronomy and Astrophysics Letters. And just my German colleague, Thomas Müller, called me and said, hey, you are in Sterne und Weltraum. And this paper was also in Nature Highlights, so maybe we did something interesting. Thank you very much.
Thank you for excellent talk. Indeed, you did something very exceptional.
Yeah, well, if you are in Sterne und Weltraum, then
yeah, and it's I'm really impressed and happy that besides the space missions, we still need the ground-based telescopes.
Yeah.
So if there are any questions, so please.
Yeah.
Is in the first slide, you say that it's complicated to obtain the measurement of faint objects with tests or trans-Neptunian objects.
Yes, it's almost impossible. Well,
why? Because
well, it's a 40 centimeter telescope, and the limit is roughly 18 magnitude. You can detect it. You can detect the object down to 20, I don't know, 20, 21 magnitude easily. But to get a photometry to derive a light curve, the limit is something like 18, between 18 and 19 magnitude, and the vast majority of the trans-Neptunian objects are fainter than this. And also the pixels are very large.
Yes, I know it was.
It's 21 arcseconds, so they get very easily contaminated by background sources.
Okay.
It's of course, if you have a brighter asteroid, it's less the concern, but yeah.
Yeah. Another question in the I think is the second slide. The data with dark energy survey.
Yes.
But why? Which mode was used?
Actually, I don't know. It's from the other groups results, so I did not.
Okay.
Well, maybe I read it in the paper, but I don't know.
Okay.
Yeah.
Well, I suppose it could be two modes.
Yeah.
For the supernova fields.
Yes.
And the Y survey. The Y survey is more or less.
Actually, I don't know, but yeah.
I have a question about the Eris density.
Yes.
It is similar to the World Comet's density, or is more similar to?
It's more similar to like main belt asteroids. So it's 2.4 grams per cubic centimeter, which is even, well, not the typical density of a C-type asteroid, which is less than this, but more towards the, like, I don't know, S-type, but S-type is typically even denser, but something between the two. So it's exceptionally dense.
Okay, so are there any questions? So if not, we can move to another talk, which will be given online by Mike Kretlow, also about the trans-Neptunian objects. So I'm not sure if we can switch to.
Okay, so, okay, I'm ready to go. So can I start?
Yes, you can start.
Okay, hello everybody. Greetings to Bratislava and online. My name is Mike Kretlow. I'm working at the Institute for the Astrofísica and the Andalucía in Granada, Spain. And thanks to the organizers inviting me for this talk. And so in the next couple of minutes, I'm going to tell you a little bit about stellar occultations, the method of stellar occultations to study solar system objects, especially minor bodies. And so I take this opportunity also to introduce you a little bit into this method because it's very powerful, and we always need collaborators and observers. And as I mentioned in my introduction, it's not only the work done by me. There are many people involved at our institute and collaborating institutes. So I'm presenting this also in their name. So just a brief introduction. I'm assuming that not everybody of you is really knows exactly what's going on with the stellar occultations. So just to explain you briefly what we are doing with the stellar occultation. So it's basically like a solar eclipse. You have the light from a star, and you have here a moving object like an asteroid or a trans-Neptunian object. And if this object is passing in front of the star, it makes a shadow on the Earth. And if you put some observers in the shadow region, pointing to the star, to the target star, and making some kind of photometry, you will get some light curve like this one, where the star disappears and then it reappears. And this time difference you can transfer into a chart length, and which you can later, if you have several observers which had positive occultations, which you can fit to the limb, to the instantaneous profile of this object. If you have many observers, you can even do with a shape. But for the objects I'm talking now about, for the trans-Neptunian objects, we usually don't have so much occultation charts, and we assume that at least the bigger ones are not irregular like small asteroids. So we fit an ellipse to this extremities to get a size of this object, which is one of the main physical parameters we are interested in. So, but you can detect many other things with the occultation method, which is very powerful. So you see again a light curve here of an occultation by the large sun tower Kretlow. And as you see, you have here secondary events, these dips. And this turns out that these are very probably rings around Kretlow, and that was the discovery occultation of this ring system. And the same happens for another sun tower called Chiron. We already had some events in 2011, an occultation with some secondary events. At that time, it was already assumed that it might be some kind of rings or shells. And some month ago, half a year ago, we had another occultation where we clearly could detect the secondary events, which we think are caused by a ring system around Chiron. The same is for Quaoar. I just mentioned it here for the TNO because this was interesting, because this ring system is outside the Roche limit, where at least up to now, we thought that it's not possible to have a ring system because of the tidal forces. So another interesting possibility is to observe and to detect the satellites or the binarity of TNOs. And this was, beside Pluto and Charon, the first occultation where simultaneously we had positive occultations of the one object of the main body and of the presumed satellite. These blue dots are these positive occultations. What do you see here? This is a nominal prediction of the TNO, where we predicted it to cross this region. That's the reason why you have here all these observers, which had a negative observation, so they did not detect an occultation. And but these observers had a positive occultation, so at the same time we could observe the main body and a small satellite of this system 2000 YW134. So to summarize, stellar occultation is a very powerful tool. You can do sizes, and that with a kilometer or sub-kilometer accuracy, and there are some kind of directly measurements. And of course, you also get, as you saw on the first slide, the shapes. And we are, especially in the case of TNOs, we are interested what kind of ellipsoids we have. The interesting thing is that we think that beginning from a size of about 450 kilometers, this bodies could be in the hydrostatic equilibrium. So the sizes and the flatness of these ellipses are interesting to us. You get very precise astrometry in the micro arc second level with the Gaia stellar catalog. And as shown in the first slides, you can probe the environment for rings, shells, satellites, and so on. So all in all, stellar occultations is a very, very powerful ground-based observing method. And it can be, so to say, very cheap, because you have to observe not the TNO, you have to observe the star. So even if the TNO has 22 magnitudes, but the star has, for example, 12 magnitudes, you can observe it with small telescopes. So this is also a very good opportunity for amateur astronomers to contribute in real science. So just to give you a brief introduction in the objects we talked about. So probably you know that in the outer solar system you have the Kuiper belt, you have the Centaurs, which are essentially Kuiper belt objects or TNO objects transferred into this region. And because I'm going to talk about one object, which is about here, it's close to this Plutino group. I choose this object because we are currently working on this object, and I also observed it with a telescope which is supported by the European Telescope Network. So in general, these kind of objects are very interesting to us because we think they are very pristine objects, the trans-Neptunian objects and the Centaurs. And but what it was already mentioned by Csaba, they are hard to observe. They are far away. So even high resolution direct imaging is very, very difficult. For example, to resolve satellites. In situ observation is very, very expensive. We have just one case, a Horizon mission, New Horizon mission, and they are faint, as mentioned in the first talk. So light curve observations are also very difficult and need usually larger telescopes. It was now interesting for me what Csaba has presented. That's very interesting to use also smaller telescopes. They also, for very precise astrometry, which we need for the stellar occultation predictions, you usually need larger telescopes to get the signal to noise ratio and so on. And they are cool. So the mean surface temperature is about 30 to 50 Kelvin. So they are, if you want to observe them in in the thermal infrared, you need to do this with a space telescope. So in the last slides, I'm going to talk about this object 2002 KX14, which is in the mid-size range, and just a moment. And so it's a cold classical TNO, and the radiometric diameter by Herschel and Spitzer was calculated about 455 kilometers. So another point is that the rotation period is yet unknown, and there was in the literature there's one observation, or one it's mentioned to have a very small amplitude, and but no period was derived. So I'm not sure. I have 2 or 3 minutes. Is that true?
Yeah, I have a couple of minutes more.
Okay, fine. So so that's in that case, we in Granada we are using, or we are monitoring TNOs, especially targets which are going to have an occultation, also for astrometry and photometry. So we have photometric observations of this object from 2012, made with the 1.2 meter telescope Alto. We made some observations also in combination with an occultation in 2021 with the William Herschel telescope at La Palma. And last year, I was able to use the Danish 1.5 meter telescope in La Silla in order to get a light curve and to a rotation period. As Csaba also mentioned, it's a crowded field, so the photometry is not easy to perform. Also low amplitude, so yet I'm not sure if we really can do a rotation period. So that's the reason why we focused currently on the occultations. These occultations are on a regular basis calculated and predicted by us, and available about different websites, on the Lucky Star website, on the Core website by myself, and so on. And as I mentioned, the prediction accuracy is very important to have precise astrometry. That's the reason why we observe them in advance. You must remember that an accuracy or an inaccuracy by 10 milliarc seconds at a distance of a TNO of 40 astronomical units corresponds to an uncertainty on the surface of the shadow path, which I showed in the first slide, of about 300 kilometers. So that's in this table. These are the preliminary results. We have all in all 5 occultations observed in the past about 10 years. In 2012, it was only one shot, so you cannot fit an ellipse to that. You just can make an assumption about a circular minimum diameter. And so this apparent diameter is about 365 kilometers. And if you use the absolute magnitude, which was also used by this Herschel and Spitzer papers, TNOs are cool, then you can calculate the visual albedo from that, and that's 0.15. And so we are for 2020 the best so far occultation observed with 10 or even 12 charts, which gave for now diameter of 393 kilometers. And we have another observation in 2019, which also allows only a circular fit. And very recently, that's the reason why I'm currently working on this object, we had a couple of weeks ago 2 other occultations observed in USA and Brazil. So where we, at least for this occultation, we can make an ellipse fit. So, but this is work in progress. So I have no results here. So all in all, we are confident that at least from the occultation we can derive some size information. We have high precision astrometry, which you can do from this occultation itself. So, and what's to do to finalize this object is to analyze the last two events and to put all this together. What you can make is you can assume a three-dimensional ellipsoid, and you can scan the parameter space and try to fit the occultation profile data and, if possible, the photometric data to get a 3-day model, an ellipsoid with some axes which fit the data, and that's what we are currently working on. So yeah, that's all. Thank you.
Okay, thank you for interesting talk and interesting results. We are a bit out of time, but I think we can have one or two quick questions, if there are any. Maybe from remote participants. So if not, maybe we can have discussion after the session.
Okay.
Okay, so we can move to another talk, which will be given by Milagros Colazo from Argentina. Mili, can you try to unmute yourself and share the screen?
So I will stop my camera because of the internet.
Yeah.
And okay, great. Well, so I'm Mili from Argentina. I'm going to talk about what can we learn by studying the brightness behavior of asteroids. This is kind of a summary of my work related to phase curves and also light curves of asteroids. First of all, I'm going to talk about the asteroid rotation, so the light curves. I work with GORA, which is a group of about 50 amateur and professional astronomers. We operate 33 observatories in different states of my country, Argentina, and also other countries such as Uruguay, Peru, Spain, and Italy. The main objective of this group is measure and publish rotation periods of asteroids. So far, we have measured 124 rotation periods, and we published 12 papers in the Europlanet Bulletin. So here's the location of the observatories, and here we can see how much we grow these last years. Well, some statistic about the group. This is the plot of diameter versus frequency for the asteroid light curve photometry database. And this one is hours. So we can see here that we have measured recently these asteroids 1093, 903 Azimuth, which is maybe one of the slowest asteroids that we have ever measured, yes, as a scientific community. So we are looking for some challenging cases. And one of them also is 2000 PQ9, which was a very poorly studied object. We couldn't find at the time any period published in literature. So we proposed a candidate period of 3.74 hours. And well, this fast rotator hypothesis is consistent with its small estimated diameter of 1 kilometer. Yes. Well, this group, as you can see, is very active. Well, we are still have observations going on and some papers in the Europlanet Bulletin, which are in the revision process. Another topic, I study asteroid phase curves, not with the amateur group. So, well, as you already know, the phase function describes the relation between the reduced magnitude and the phase angle. Yes, we can describe this behavior with different phase functions. For example, the AG or the AG1, G2. And for this kind of studies, we developed a Python package called Piedra or Piedra. We have Piedra in pip and also in GitHub. If you want to collaborate or see the software, you can go to our GitHub and leave your comment there. Piedra is a Python library that allows to fit 3 different models of asteroid phase functions to your observations or any catalog that you want, maybe Gaia catalog or the Sloan catalog, yes. The input file must be a .csv file with 3 columns, the MPC number, the phase angles, and the reduced magnitude in the web filter. And then Piedra can fit 3 functions, which are the AG, the Shevchenko, and AG1, G2, yes? And in addition, the input data can be plotted with the chosen fit. Piedra is very simple to use. The first thing that you need to do is import the libraries, which are Piedra and Pandas. The next thing is load our data with Pandas. And then if, for example, you want to feed the AG model, you need to invoke Piedra's AG fit function. So you just do piedra.agfit and you give it the data frame, yes, and it's done. So only with 3 steps, you can have your HG catalog of phase function parameters. And as I said before, if you want, you can plot it with another function of Piedra, which is ag.plot. We try to apply Piedra to larger data set, which is the combination of Gaia DR2, DR3, and Sloan. And also we analyze if this kind of combination is worthy. As you see here, Gaia DR2 observes kind of brightest asteroids than Gaia DR3 and Sloan. And about the phase angles, we know that Gaia observes only at large phase angles, but Sloan has very good coverage. The problem is that for Trojans, Sloan only give us 1 point in the very small phase angles. And the other problem is that if we want to study the targets of the Lucy mission, we only found these 3 in Gaia DR2, but they are not present in the other catalogs. And this kind of fits with only 1 point here and this data with so many dispersion of the Gaia, it's not so reliable. But if we analyze the H and G distributions of the Trojans and we compare the L Lagrangian point 4 and 5, we can see there is no difference between absolute magnitude and the slope parameter. The last thing is work about asteroid taxonomy using unsupervised machine learning algorithms. The great advantage of Sloan is the set of 5 filters that allow us to study taxonomic analysis. However, until now, the color variation produced by the change of phase angles of the object has not been taken into account. So our approach was to address this issue by using the absolute colors of asteroids. And so we are unaffected by variations caused by the change in phase angles. To do that, we use the absolute magnitudes calculated by Álvarez-Candal in 2022. And the taxonomic classification of Carbano and collaborators using Sloan is widely accepted. Nevertheless, their scheme has asteroids with multiple classifications, so we would like to address this issue by applying our approach. So the first step in this work was to determine which parameters.
Sorry, Emil, I'm not sure if we are on proper slide. We can see still slide application problem Trojan space curves. Shall we see this one?
Here? No? Maybe it's my internet connection.
Maybe you should stop sharing the screen and start it again. Maybe it will help.
Here?
We don't see it yet. No, we still can't see it.
Okay. I will try again. Share. Now?
Oh, something is happening. Oh yeah, we can see many of slides.
You can see it. You can see only one slide.
Yeah, now it is okay. Now we can see the first step.
So, well, yes, first step, yes. Well, so the first step is to determine which parameters best describe the set of observations. So we look which combination of colors best separate the taxonomic types. And we found that the HG minus HI and HI minus HZ were the best colors that separates our clusters. And also we noticed that usually other authors implemented principal component analysis to obtain this color A. But this color A that is usually used is correlated with the HG minus HI color. And so we prefer to use the HG minus HI color because we don't have to compute the principal component analysis, so we are reducing the computation time. The second step is to apply the soft clustering algorithm to identify the probability of each object to belong to a particular group. So we use the cyclic fuzzy semins. Here is the result. We obtain these clusters. We identify only the first the most important four clusters, and we classify 9,481 asteroids, 6,000 about with a probability greater than 60% of belonging to the assigned cluster. And the ones that are classified with probability less than 60% obviously are the ones that are in the zones where merging of clusters, you know, where mixed. And well, the third step was to perform the reclassification of the ambiguous Carbano asteroids. So we can classify 134 asteroids with more than 60% of the ones, the 270 asteroids that Carbano, for example, has as ambiguous classification. And we can see that many of them are very far away of the C or X type that the other authors proposed, yes? The same with the SV and XS ambiguous classifications. And also we identify B-type asteroids outside Vesta family that is already known. For example, Eunomia, Eos, and Coronis were proposed as parental bodies of these B-type asteroids outside the Vesta family. And we also compare these black photospectrums are the one of obtained with Sloan data. And we compare this photospectrum with the S-2 spectra. Yes, and well, we can see that our sample is more related to Ernie or Peter spectra, and they're not similar to the one of Vesta. So thank you.
Thank you for a nice talk, excellent work, and amazing number of data. Do we have questions for Millie? If not, I've got one. Do this GORA association make also the phase curve, or they are interested only with determining the rotation periods?
No. Nowadays they are not studying phase curves, only rotational periods.
Yeah. Okay, so thank you, Millie, again, and we can, yeah, and see you in a few weeks in Poznań. And
Yes.
so
I will see you soon.
Yeah, so the next speaker is Krzysztof Kamiński, who will be talking about the minor body, but this time the artificial ones.
Okay, can you see the first slide?
Yes, we can see it.
Okay, great. So, good afternoon, everyone. My name is Krzysztof Kamiński, and I'm from Astronomical Observatory of Adam Mickiewicz University in Poland. And I would like to tell you a few words about the influence of artificial Earth-orbiting satellites on astronomical optical observations. Well, the fact that a satellite trail can contaminate astronomical image is well known, and it's nothing new. But a few years ago, the interest in that topic sparked significantly, especially when this image was published, when a survey telescope, relatively large aperture, 4-meter telescope, have recorded 19 bright satellite trails on a single image. These were Starlink satellites recorded here, and it was kind of a special circumstance. It's not a common situation as of now, fortunately, but because of that, it raised some concerns. What we can see here is a group of Starlink satellites just launched a few days before, so they haven't separated. They formed some so-called Starlink train, and so that's why there were multiple of them were recorded in a single exposure. Fortunately, other exposures from the series of images was okay, actually. So the concern is substantial, also because the number of artificial Earth satellites is rapidly growing, especially in recent years. Overall, here on this graph, we can see the whole history of space, space satellites. The number of cataloged space objects. By cataloged, I mean unclassified, and those which have at least 10 centimeters. Smaller are not regularly tracked. So here we can see a steady growth of the number, and with some jumps because of fragmentations, like collisions or deliberate weaponry trails. But in recent years, we can see a rapid increase in the number of satellites. Here, right now, it's about 27,000. and still growing. The growth is mostly in low Earth orbit region, so the satellites below 2,000 kilometers above the ground, and it's mostly accelerated by the growth of Starlink megaconstellation, satellite megaconstellation. So a few papers have been published analyzing the situation. Here we can see the summary of what was predicted in 2020. So how the satellite megaconstellations can grow, and adding SpaceX Starlinks and other projects together, the authors concluded that we can expect, well, basically doubling the number of satellites in the near future. And moreover, most of the satellites, as it's visible in the last column, are, well, all of them are very bright when they are outside the Earth's shadow. Some of them are even visible to naked eye, some not, but all of them are very bright for astronomical telescopes. Fortunately, because of the geometry, all of these are on very low orbits, and most of them are only visible during the dawn and dusk. So observations during midnight are not affected by these constellations. And because they are on very low orbits, only a fraction of them is observable. For example, the first shell of Starlink satellites, which is composed of over 7,000 satellites, contribute only to roughly 13 satellites visible on the sky at any given moment. But satellites on higher orbits are contributing much more, and totally it's over 250 satellites visible all the time when they are not hidden in the Earth's shadow. So a typical image of what we can expect on the sky is something like that when we are near the midnight. Here is just an example from a random location when the solar altitude is relatively low, so we are close to midnight, and only satellites above 30 degrees altitude are plotted here. And we can see that, well, in that region on the sky, we can detect roughly 650 satellites. Of course, the number will vary during the night. And most of them are on higher orbits, because those on lower orbits are hidden in the Earth's shadow, fortunately. But still, we can see that some regions, like geostationary belt especially, are populated very densely with Earth satellites, and most of them are very bright targets for astronomical telescopes. When we are closer to the beginning or end of night, the situation is changing. So now we can see when solar altitude is minus 12 degrees, that a large population of low orbit satellites is visible. It's marked by red. The lines are representing the trail of that satellite made during 10 seconds. So they are moving very, very fast. And even though they do not, they are not dominant on the sky, they move very fast. So the probability of affecting an image is actually quite high. When looking at the brightness distribution of satellites, of known satellites cataloged, those for which we have some data, we can see that, well, on this image, we can see satellites to the left, the very low satellites with low orbital period. These are the low Earth satellites, and they are, well, most of them are between 12 and 13 magnitude, but a significant fraction is much brighter as well. And other satellites are at roughly the same level, slightly dimming when they are farther away simply from the Earth up to the geostationary belt. They also differ not only with brightness but with angular velocity. Of course, the low Earth satellites are much faster on the sky than the higher or objects. So even though the geostationary satellite might be dimmer, it's moving slower, so the trail on the image can actually be brighter. So because of that, it's not that easy to actually predict whether a satellite will be detectable. It's not that obvious, judging just from the magnitude of that satellite. So what can be done about this? On one side, there is a good news that Starlink constellation is being modified to actually reduce the brightness, the observed brightness of these satellites. Initially, it started with dark sats, just painted in black. Then some other measures were introduced, some materials, special materials coating, different orientations of the satellite and its solar cells. And overall, we can see a slight decrease in the observed magnitudes compared to the initial batch of satellites. And recently, a second generation of Starlink satellites has been announced. They will be significantly larger, so potentially brighter. But fortunately, because of all those measures, the brightness will be hopefully keep in check. So we expect something on average at the level of 7 magnitude, but it was not as yet confirmed. And in the middle, you can see our own image of one of the first Starlink satellites, which was observed at 4.4 magnitude. Of course, those magnitudes are very variable, depending on the orientation and illumination of the satellite. The other thing that can be done, well, we can actually predict whether our observations will be affected or not by satellites. Most of the satellites have publicly available orbits, not very accurate ones, but accurate enough to do such calculations. Therefore, we started a service, an internet service available for everyone. We call it Satellite Trail Predictor. And here you can see an example output of that service. If you put your data there, like coordinates of your observatory, exposure time, etc., you can calculate what should be in your field of view within a given period of time. And as you can see here, this affected image could have been easily predicted, although as it's clearly visible, the trails are not exactly in the predicted positions because those satellites were actually changing orbit during that time. At the end, I would like to show you an example of a series of astronomical observations that were significantly affected and, well, astronomers were confused by what we believe was an Earth-orbiting satellite. This is an example from 2020 when a publication was, a paper was published showing an investigation of a high redshift galaxy candidate, GNZ11. The candidate was observed with Keck telescope with a spectrograph, multi-object slit spectrograph, and one of the objects was this galaxy. It's a very distant and dim target, therefore on a single spectrum we cannot see anything. Only stacked images revealed the spectrum of the galaxy, but on one spectrum, the galaxy or its spectrum was actually clearly visible, much brighter than what was expected. So they call it this spectrum a flash because the target apparently increased its brightness significantly. And after analyzing the data, they concluded that just by luck, they most likely observed a very distant gamma ray burst, which would have a similar characteristic of just brightening for a few seconds or minutes, depending on the type of the burst. And that was their publication, the main conclusion. So that was actually the candidate for the most distant gamma ray burst ever observed at that time. So, well, we looked at it and used our service and our software to actually verify that discovery. And we quickly found that, unfortunately, there is a satellite, Earth-orbiting artificial satellite, that could have produced a similar flash in one of the spectra. Exactly at the exposure time, one of the catalogued satellites, Breeze M, was going in the field of view of the Keck telescope. It was not going exactly where expected. The flash occurred in the center of this image, where X is plotted, and the nominal orbit of the satellite was slightly above. So it was not even crossing the slit, the central slit of the spectrograph, because those blue lines are where the slits were positioned. But the uncertainty of that orbit was quite large, actually. So within 1 sigma, it's perfectly possible that the satellite might have been crossing this slit, especially that it was not observed on other spectra during this exposure. And moreover, subsequent orbits, which were improved after that event occurred, also were closer to the position of the target observed by that group. So we started to looking at that satellite more closely. It's a fourth stage of a Russian Proton rocket. It has quite a regular shape without any mirror surfaces like solar arrays. Therefore, we conducted some observations of that satellite and calculated its absolute magnitude. And using that observations, we could calculate what was the magnitude of that satellite during the observations of the flash. And taking all the data into account, it was a perfect match. The satellite was roughly at 10 magnitude, but it was visible in the slit of the spectrograph only for a fraction of a second, so it could very well easily looked like a target of 19 or 20 magnitudes, as was estimated the magnitude of the flash. So, concluding, after our investigation, we revised the distance to that flash by 20 orders of magnitude from one of the most distant object in or even in the universe to one of the closest, actually. So that's a great example. Unfortunate. What we can expect, especially when all those constellations and mega constellations will be deployed fully, as expected in a few years. And that's all from my side. So thank you very much.
Thank you, Krzysztof, for a very nice talk. And there is a time for a question now. Yeah, we've got one from Csaba.
So is there a study focusing on the thermal infrared?
Did you hear? Are there studies focusing on thermal infrared? That was the question.
Oh, I'm not aware of that. Okay. So yeah, that would be.
If I may, so because first if you modify the satellite in a way that it's less visible in the visible,
Mm-hmm.
then it will be brighter in the thermal infrared.
Mm-hmm.
First. Second, they will not only be visible at dusk, for example, but during the whole night because of their thermal emission.
Yeah, that's right.
And I know that probably there are a smaller number of observatories working in the, I don't know, 3, 4, 5 micron regime. But as you have just shown this example, it can very easily be that the same thing is cause a false detection of whatever, but not in the visible, but in the thermal infrared.
Yes, I totally agree that yeah, especially those low satellites would be visible all the night, and yeah.
So you are not aware of any studies?
Unfortunately, no. But we are working in our service that I was mentioning to provide also data for satellites which are within the shadow. So that would be soon available on our side.
Okay, so I could make predictions for the thermal infrared. So maybe we can discuss it offline.
Okay.
Thank you.
Okay, thank you. Do we have any more questions? So if not, let's move to the next talk, which will be given by Emil Wilawer about our alert system.
So, hello everyone. My name is Emil Wilawer. I'm from Adam Mickiewicz University in Poznań, and today I'm gonna tell you about PARSEC alert system, which I've been working on for a while. I will try to catch up with our schedule a little bit. So, what is the main idea behind the PARSEC? It is a service which is a tool for coordinating the observation of the solar system objects, and not only a solar system, but in general observations for observers and researchers around the world. Users can create some observational campaigns with requests for specific objects that they're interested in. And the tool is provided with some alert system and email notifications. So the system is currently in development stage. So not every feature is working right now, but it will be soon. So the main part is alerts. So for now, we're collecting, observing alerts from Exoplanet team, and we are putting the information on the main page of PARSEC alert system with all the details about given requests. So another thing is that users who are registered into the system are able to create their own requests. Like they're putting the target which they are interested in, the range of dates and times, and they can provide some description to specify more why they want to observe or in which, like for example, filters and such. And here the example of the created requests. So you can see the request for a given target. Requests can be a part of bigger campaigns. So for example, we can see that Eros, Kortuza, and Kortuza, Eris, and Ceres are within one campaign. So you can group the objects that you are interested into one campaigns. And you can see how many users are following your campaign, and if there are any comments about that object or campaign or request. Yeah, so this is the view example of request for Eros. the dates that user is interested in, and there is one user following that request. Under the request page, there is a comment sections in which users can exchange some more informations and details, also add some remarks. This is a view for campaigns, and you can see how many requests, so how many objects are a part of such given observational campaign that users created. Here we can also have a subpage containing some useful services about like plenty of different astronomical oriented topics like asteroids, planets, exoplanets, comet, and such. So if you have created such some small service and you want to make sure that the community will know it, you can write to me or Edyta, and we can include your service here to spread the word about your work. Yeah, we can also users have also their user profile when they can like select their image profile. They can also add locations, because when you are user who would want to participate in such campaign, you could find, well, you can define locations of your telescope, your observing site, and PARSEC will allow you to search for requests that you're able to observe from your location or locations. You can add as many locations as you want. There's also a hidden functionality of PARSEC alert system, which is a Europlanet Telescope Network file repository. So as you probably know, there are plenty of proposals going on using the telescope network, and the data are supposed to be shared through the VESPA service. So to make it easy for participants of telescope network group, they can send us the files, and it's our job to make them visible through VESPA service. So as I mentioned, it's a hidden functionality. So if you are a group, a member of Europlanet Telescope Network, you would have to, despite the registration using the webpage, you would have to send us an email so we could like allow you to use that part of PARSEC service. And here you can see the example of uploaded files. Files are grouped into datasets. So if you have observations of some object from one night, you put all the FITS files into one dataset, and you can manage those files through that service also. Providing some like metadata, so to help us to prepare the data that you send us to be visible through VESPA. And this is the URL of the service. So it's parsecs-europlanet.eu. So I really encourage you to register to that website. And when we finish development stage, we'll start a testing stage. We will notify you, we'll send you an email that we will want you to actively use that website and give us some information or comments, what could be implemented, what could be improved. So the service will be more useful and expand its user base. So thank you.
Yeah. Virginia have a question.
Yeah.
I would like to ask, this is your service to request for observations. So is it possible to request for CCD images, for photometry, for spectroscopic observations, one question, and another question: for which objects it is possible to request observations?
Oh, it's all up to
for asteroids, for stars, for what?
It's all up to you. You are the one who decides which object are you interested in. You can just put the name of an object and some time frame and details.
But do you know information about the community which could provide those observations? Are they also registered?
Yeah, they also register. So there are like two types of user: the one who are looking for help with observations, and another users who have their telescopes ready and they want to find some objects to observe if they want.
So do you have some information of those who could provide, who promised to provide what telescopes are available, what instruments?
Oh, that's a good point, to have some like informational part in which users could describe their hardware. That's a good point. So not only the location, but some technical details. Yeah.
Okay. It would be useful for those who request, because we can ask for something and nobody can do that.
Yeah, yeah. So any more questions?
So if not, we can move to the last talk, which will be given by myself. Okay, thank you. And I'm going to talk about the Gaia-Ground service, which is one of the services included in the PARSEC alert system. And the Gaia-Ground service is a Gaia-Ground-based observational service for asteroids. And this is the service that was created as a result of collaboration between researchers at Adam Mickiewicz University, between European Space Agency and private IT company. And this service is dedicated for amateur observers who want to support the researchers in doing the observations of asteroids, and they can support us in two ways. First of all, doing the occultation event records, as Mike was telling about today, and doing the photometric observations. And we've got plenty of such observations, and they were already used to support Horizon 2020 project SBNAV and to support a large program which was held on the VLT Sphere telescope. So the data were already used in a very practical way. So if you go to the web page, you've got the table with the list of asteroids for which we currently need the observations. And these asteroids are sorted in the order of priority. And we've got the basic information: how long this object is going to be visible, what's the range of the magnitudes, and how many percentage of the light curve we have already covered. Because what we need the full rotation periods covered. And moreover, we provide even the information at what time the specific night that the observation should be taken in order to cover the missing parts. So it's very useful for planning the observations. And the Gaia-Ground was created in order to support the Gaia space mission. And thanks to the contacts with people from Gaia mission, we've got the prediction, and we show on the service which asteroid is currently observed or which is going to be observed in the near future. And the observations taken from the ground exactly at the same time as Gaia observed are particularly variable, because from ground we have differential light curves. And if we have the measurement of Gaia provides us single points, so we can calibrate our ground-based measurements to the Gaia point. And this way we've got the data calibrated to one photometric system, which is particularly valuable later in the spin and shape modeling. We also provide the information about occultation events. If there are any important ones, we provide the geometry of the event and the duration, and we provide information which asteroid is occulting which star, such that the user can do the observations. I'm not going to talk about why we need it because Mike nicely explained everything. So we are trying to keep the service as much user-friendly as possible. So we've got the observation planner where you can choose your observing site, the country and the city, range of magnitudes in which you can observe depending on your equipment, and the begin and end date when you can observe. And then you've got the list of objects which are visible from your location. Then you can choose one or more of them which you are going to observe. And then system moves you to more detailed information when you can see the right extension, declination, elevation, azimuth, and how long object is visible on the sky. So there is the time of start and end of the visibility, and of course magnitude. You can also plot more detailed charts showing how the object is, how the elevation is changing with time, or how the azimuth is changing with time. You can also see the sky view showing how the object is moving on the background of the sky field, which helps to plan observations and prevents from a situation, for example, when asteroid is moving through the bright star and things like this. And so we've got the planner in, and we expect that observer is taking observations, and then the observations can be uploaded through the upload panel in our service. And if there are some observations, we see that we've got a new set of the data, and then the data are reduced and photometry is done by people in our observatory, mainly by me. So, and then observers can see what they have produced. They can see the nice light curves from the data they have provided to us. So Gaia-Ground started to work at 2016. Since then, we've built a quite large group of users. We've got more than 180 users, which provide us almost 1,000 nights of observations. The most active user provided more than 250 observations, nights of observations, which means that he spent with the telescope something like 2,000 hours observing for Gaia-Ground. So this is really impressive work. And here are the results. A few results of coordinated observing campaign, few examples of light curve composites, which were used to determine the precise radiation period. Here we can see the different shapes of the light curves for Cassandra, Palma, Polyxo, and Chloe asteroids, which were obtained thanks to the effort of Gaia-Ground observers. And the project lasts few years, so for some objects we are able to gather more than one full rotation period. So here, for example, you can see how the light curve changes from one to another opposition, which means that geometry of view is different and we see different parts of the asteroids, which is really important information for spin and shape modeling. And here is similar example for Karlova. We've got the data from two oppositions. So far, the data have been used to calculate asteroid spin and shape models. In SBNAV project, we've calculated their models for 15 asteroids. And it's worth to say that these are non-convex models recovering some cavities and other non-convex features on the asteroids. And the data supported also a large program in which we used adaptive optics imaging from observations taken at VLT telescopes. So all these projects resulted in several papers published in Astronomy and Astrophysics monthly notices, but also in Nature Astronomy. And of course, the observers are listed as co-authors of these papers. And here is just to show our models produced for Egeria and Julia asteroids and the synthetic light curves from these produced models. So the service is working really nice. So we think it was a great success to launch such service, and we still encourage people to join and do the observations and share their experience because it's not only good science but also real fun. So thank you. And if you have amateurs, then to see and join the Gaia-Ground. Thank you. Do we have any questions? Yeah.
When you have the participation of the amateurs, how is how do you do if when you are going to publish an article, you put everyone that participates doing the light curves? How is the
no, if you use the light curves from one it depends who provides us the light curves. If one observer provides the light curves, he or she is included as a co-author. If we don't use this particular light curve, it is not included. So if someone's data are used, this person is for sure included in the paper. That is our policy, and I think this is the fair things of doing things.
So I have a question about the basis of users, the amateurs that you are contacting to, and they are working in this project. Do you have difficulties to find collaborators in some places? Is this mainly in Europe? Do you have people from other locations?
Well, they are mainly from Europe, but we've got some people also from South America. Yeah, but this is mainly Europe, and we see I would say a large of rotation. People are coming, doing observations, then they are moving to observe some other object, then they are coming back, and things like this. And there is a large, I mean, not large, but the most difficult thing is to encourage people to observe regularly because they are jumping from one interest to another. Because I realized that doing asteroids with known rotation periods again and again and again might be quite boring, but from point of view of scientists, they are really important. But we need observations from few oppositions in order to make the spin and shape model like this. So for amateurs, maybe quite a bit boring to waiting few years because before they will see the final results. Yeah, so this is the main difficulty. Okay, are there any questions maybe from remote participants? And if not, so thank you for being here, especially that it was extremely difficult to organize this session of minor bodies, as exactly at the same time there is this huge conference, Asteroid, Comets, Meteors in Flagstaff. So our people related to minor bodies are probably there. So thank you that you have been here.